Good, this is working. Okay, so I'll start, as I said, with Markov chain Monte Carlo. Markov chain. Monte Carlo. This is section, in my notes, this is section 2.8. Okay, so this is part of chapter 2 on discrete time Markov chain. So we'll be dealing with the discrete time Markov chain. And so this is section 8 in chapter 2. So I'll motivate the technique with an example, which is the estimation of pi. There's a statistical way of estimating the constant pi, 3.14, which is you take a square which is centered with -1, 1, -1, 1, like this, and then you put the circle. I should have put the circle first. And what you do is that you just put points uniform at random in the square, and then you count the fraction of points that will fall into the circle. So what you're doing is that you generate independent points in the square uniform. So you have x1, x2, and then we're going to have xl. So I have a sample of uniform points in the square, and the estimator of pi. So I'm going to write pi estimator for the sample size L is 4 times divided by L, the sum from 1 to L of the indicator function for falling into the circle. So you count the number of times I is part of the circle. Okay, so you have all your L points. Some are in the circle, some are not in the circle. They're uniform on the square. If you take the sum of all the points, so that's the number of points in the circle, you multiply by 4 and divide by L. This is the fraction of points in the circle multiplied by 4. You get an estimation of pi. If you have 1 point, it might be in the circle, it might be not in the circle. This is not going to work. If you have 2 points, you get a very poor estimation of pi. But if you have 1,000,000 points, 10 million points, 1,000,000,000 points, it gets closer and closer to pi, and then you can study that convergence using what we've seen yesterday about sampling. Okay, so this is the basic Monte Carlo sampling to get an estimation of pi. It's a cute example where you get a better approximation of pi as the number of points goes to infinity. And this makes sense in a geometric way. I'm not going to explain why we have the 4 there. I think you can see it with the area, the probability to hit the circle is the area of the circle divided by the area of the square. And so this is why I have 4. Okay, now to do this, you have to be able to generate independent points uniformly on the square. There's another way that you could do this, which is the second method. So what you do instead is you have your circle, you have the square, and what you do is that you build a random walk instead in the square. Okay? So what you do is that you start with a point, and then you're going to generate a new point, and then you generate a new point, new point, new point. So instead of drawing points at random, just dropping points at random, you just generate a random walk on the square. So what we're going to do is we'll generate a Markov chain. So instead of generating a sample of independent points, I'm going to start with the first point, then I generate a second point, and I generate then L points. So this will be done with a Markov chain. And then we're going to have the estimator for pi will be the same. We just generate we calculate the estimator as 4 times the fraction of points that will fall into the circle. So this is the estimator. I want now I to be in the circle. Okay, so this will be now the number of points or states in the circle. So it's the same estimator, but the underlying points that are generated are completely different. They're generated as a random walk, which means that we're going to generate them as a Markov chain. So this method with independent points is just normal sampling, statistical sampling, or you can say this is just normal Monte Carlo. This now here is Markov chain Monte Carlo. It's a different techniques for generating the points. So overall, the goal, okay, so this is a basic example where I want to generate points that are uniform on the square. And I can either draw points if I have a generator, a uniform generator on the square to do this, or I can build a random walk that will give me that uniform distribution of points on the square. In general, so this is just a specific example, in general, what I want to do is to generate points according to a given distribution. So I want to generate points, or what we call them variates, so realizations, points, values, from a given distribution F or P. Here I'm gonna write P of X. That's what we call the target distribution. There are many ways to do this. There are many ways discussed in my notes to do this. And we have many random number generators to actually generate variates according to a specific distribution, like random n, for instance, gives you values distributed according to a Gaussian distribution. That's good. In many cases, a distribution is very complicated. So the idea of Monte Carlo, so the Markov chain Monte Carlo, the idea of it is generate or simulate a Markov chain having P as its stationary distribution. Having P of X as its stationary distribution. Okay, so this is the numerical goal. Devise a Markov chain, a random walk, a Markov chain in general in discrete time that will have that target distribution as the stationary distribution. So as you run the Markov chain in simulation, the points that you will generate will have asymptotically that distribution. So that's the trick and that's the idea. Okay. So I'll present one recipe to this, which is called the Metropolis algorithm. It's not the most general, but it's just easy to present, and it's the one that physicists use the most.
Hugo, there's a question. See, like in this example, I guess the random sampling is more efficient than this Markov chain Monte Carlo. But I guess there'll be some problems where Markov chain Monte Carlo will be more efficient, right?
It will be more efficient when have a look at that px. So what I want to generate, I want to generate values of a random variable distributed according to this px. So imagine that the px is just an exponential distribution on R. That's easy, I can do this. If px is just a Gaussian distribution on R, that's easy, I can do this. But imagine that px now is a multivariate Gaussian distribution in 10,000 dimension. There's no way I can actually write down a black box routine that will give me values of that distribution at random. But the Markov chain Monte Carlo will be able to do this, okay? Because it's a simple method, and the difficulty is finding a Markov chain that's going to have that distribution, but that's fairly easy. I'm going to show you how to do this using Metropolis. So Markov chain Monte Carlo is used all the time, for instance, when you want to sample the distribution of a many-body system, like a spin system or a gas, when you're doing simulations of equilibrium system, you use Metropolis. Because in that case, the Px that you want to sample is a kind of Gibbs distribution. And X, in that case, is a configuration involving many particles. So the Px is a very high dimensional object, and so there's no like off-the-shelf routine for giving you variance according to that distribution. So instead you use Markov chain Monte Carlo. So there are two ways you can go about generating variance according to some distribution. If the distribution is simple enough, then there are various techniques like inversion, transformation of random variable, rejection that can be used to find variance according to some distribution. And I describe some of these techniques in chapter 1. So I've skipped this actually this week, but there are more sections in chapter 1 where those methods are described. But as soon as if Px is now high dimensional or it's too complicated to represent, then Markov chain Monte Carlo is the method to use. Okay. So of course, for the simple example of the pi estimation, it's a bit of an overkill to use Markov chain Monte Carlo, but it's quite nice to do this. And this is part of an exercise in the coursework. There's a question here, in Markov chain, how are the x1, x2, xl related? So they are related by a transition probability that we want to write. So this is a Markov chain. So in order to describe the Markov chain, I need to specify that transition probability, and this is what I'm going to do now. So the algorithm I'll present is what we call the Metropolis algorithm. It's not the most general. There's something called Metropolis Hastings, which is more general, but I'm just going for a simplified version, which is the Metropolis. So the input, again, is that you have that target distribution, which is P of x. X can be a discrete random variable, or it can be a continuous random variable. It doesn't really matter. What you do is you take an initial state, which I'm going to write as x naught. This is the initial state of the Markov chain. And then you generate a new state, which we call a move or a try. And in the simplest way, what we're going to do is the move will be the initial state plus some random displacement. So a bit like a random walk. So this will be a random displacement. And that random displacement has a distribution. And we'll take that distribution to be Q of x. And here the requirement is that this distribution has to be symmetric. Okay, so we just add a random displacement to our random initial state, and then we do this with a distribution which is symmetric. So the easiest case will be a Gaussian displacement with mean 0 and variance 1, for instance. And what we do then is we accept that move or do not accept that move according to a transition probability, which is also called the acceptance probability. So we're going to do the jump from x0 to x1, and so that's a transition probability that defines a Markov chain, and the formula for the transition probability is the minimum between 1 p of x1 over p of x0. And so you calculate this probability, that's the acceptance probability, and now you throw a random variable to see if you accept this, and if you accept this, you just override a new state, x1, accept x1, so x1 is the new state if a move accepted. Sorry, I'm a bit low now on the board. Move accepted. Okay, I'll present the code for this. Okay, but this is the algorithm. So again, the goal is to sample a random variable according to some target distribution. We build a Markov chain for this. The Markov chain has an initial state 0. It doesn't matter what the initial state is, because the Markov chain is ergodic. What we do is that we propose a new state by taking the initial state and adding some displacement according to some symmetric distribution. So here we add a random number according to some distribution, which is up to you. That Q actually you choose yourself, as long as it's symmetric. And then we're going to accept the jump as a Markov chain according to this probability. So this is the probability for the transition from transitioning from any state, initial state, to another state, or this is the probability to go from the present to the future as in the Markov chain. And if you accept the move, then x1 is the new state, and then you repeat. And so with this, you're generating a sequence of values that are forming a Markov chain. Okay, now the properties of this is, and this is part of the coursework number 2, the properties is that Px is the stationary, well, so actually I should say first, the Markov chain, so the metropolis Markov chain is ergodic. And the stationary distribution is the target distribution. Okay, so that's the goal. We've constructed the Markov chain that has that target distribution as our stationary distribution. And this holds whatever the choice of Q here for the displacement, as long as Q is symmetric. If Q is not symmetric, then you have to actually consider something else, which is what we call the Metropolis-Hastings algorithm. Another thing is that if you have a look at that transition probability, which is, so that's the transition probability, this is the minimum, as I said, of 1, P of J, and P of I. This defines a reversible, defines or satisfies the condition of detail balance. Okay, so satisfies detailed balance. And then we'll see in the second part of the course today what I mean by detailed balance. So this is a very important property for actually proving that the target distribution is the stationary distribution. Okay, I'm not going to prove this or this. This is part of coursework number 2. So the first few questions about the theory and for chapter 2 are about the Metropolis algorithm. So I would suggest that you have a look there, and then you have the solutions for that coursework, so you have the proof of these properties there. Okay, it's fairly straightforward, and it's not very difficult. Okay. Let me write a code now for the Metropolis. So I'll write the code for this algorithm. So maybe I should actually erase this because I want the little steps here to explain what the algorithm is. So let me write the pseudocode. So I'm not following any particular language, I'm mixing some language here. So what I have first is a number of steps for the algorithm to run. So I want to generate 1,000, say, random variates or 1,000,000 random variates. Okay, so this will basically determine the time that you'll be spending computing. I'm going to have a sample, a vector, which is initially empty. And then I'm going to have an initial value, maybe like 2.0, it doesn't matter. And then I have to go in a loop to do that repetition. So I'm going to have a loop from 1, 2, and steps. And what I do is I propose a move, which I'm going to call xp. xp is x plus a certain displacement, which is random. So here, let's choose just ran n. So I'm just pushing the point with a random Gaussian displacement of mean 0 and variance 1. This displacement is given from a symmetric distribution, the standard normal distribution, so that's good. Okay, but I could use a uniform between -1 and 1. I could use a Cauchy distribution. I could use anything here as the random displacement, as long as the distribution of that random displacement is symmetric. Okay, then I need to see if I accept this. So the trick to accept this is I just get a uniform random variable, and if r is smaller than the minimum between 1 and p of xp divided by p of x, then I accept the move so that x becomes xp. Okay, so here I override x, I accept the move. And then at the end, what I do is that I'm just putting this to the x sample, so I can append x to the x sample. So I'm just putting this in my vector of sample. Okay, and that's it. So it's very simple code to implement this. Again, number of steps, the number of iterations that you'll be running, and so that will give you the samples that you have. At the end, the size of the x sample will be 1,000,000. In this case, the size n step. I go into the loop for repeating the different steps. I propose a move by taking the state plus a displacement, and then I see if I accept, I see if I do a jump according to the Markov chain. And the way to do this is I compare a uniform with the probability. Okay? This is a trick that is very common. If you have 0, 1, and then you have a certain probability p here, if you throw a uniform random variable between 0 and 1, the value has a probability p to fall into that interval. So the uniform will have a probability p of being in there between the min, between this, to be smaller than the acceptance probability, and so you'll be accepting the move with that probability. Okay? So this is the numerical trick to actually generate something according to some probability. And then at the end, you're just appending this to your vector, and so you build gradually that vector of samples, which in the long time limit, so if n steps is very large, those values inside that sample vector will be distributed according to p. Okay? Note that px is actually given, right? You need to be able to calculate that px. The goal is not to calculate the px, the goal is to generate random variables that have this distribution. So px is given. You have to be able to calculate it because I need to be able to calculate the acceptance probability. Again, the goal is not to calculate px. The goal is to generate variates that have this distribution. Okay. Okay. So this is very useful. Maybe I have a few questions here. How is the distribution given as input? You have that distribution px. The goal is to sample according to px. So px is given to you. It's known to you. Do we need to demand that this stationary probabilities distribution is unique? It's unique by construction. The Metropolis algorithm, if you actually use a symmetric displacement, is ergodic. So it has a unique stationary distribution, which is the target distribution. That's always the case. Suppose delta x is Gaussian. How do we choose the variance? It's up to you. And then actually we'll maybe I'll show an example just in a minute. The displacement must be big enough but not too big, because you need to accept that move in certain cases. If the displacement is too big, then often what happens is that you never accept the move. If the displacement is too small, you always accept the move, but you're not moving much. Okay, so maybe I'll illustrate this by going back to the pi example. So this is a question. It's the same question as asking, what is the Q distribution that I need to use for the displacement? This is up to you. There's some good distribution and then there's some bad distributions. So for the Gaussian, there's a good variance and a bad variance, and then we'll get to see this. What advantage do we have for this algorithm over the usual rejection method for Monte Carlo method? For both cases, we're defining the function for the probability Px. Yes. Rejection is another method to generate random variance according to some distribution. The problem with rejection is that it's not so easy to implement when you're dealing with a high-dimensional system. The advantage of Metropolis is that there's no complexity inherent in the method. Even if X is high-dimensional, you can do this, and then it's all about generating a displacement, a move, and then accepting the move or not. So it's a very simple method. I much prefer that method actually from experience, this method compared to rejection. Okay? It's kind of an easy method that converges really quick. For generating new configuration, what random number should we use? Uniform, Gaussian, or something else? It's up to you, and then you can try different distribution for the displacement as long as it's symmetric. So you cannot use, for instance, a uniform 0, 1 for the displacement because this is not a symmetric random variable. Its distribution is not symmetric. So Q is up to you. The target is not up to you. This is what you want to generate variance from. But the Q here is up to you. So you have lots of freedom in actually putting displacements there. Okay, there has to be a fixed distribution. Okay, let me have a look with, let me actually apply this to two examples. The first one, let's go back to the pi example. And this is part of the coursework. So one question of the coursework is to implement the Markov chain Monte Carlo method, the Metropolis method, for the pi example. So again, the idea is that you have the circle, and then it's inscribed in a square. And what we're doing, sorry, the drawing is not so great. We start with some initial point, that's x0, and then we have to generate another point. So to do this, what I can do is, so I have a number of steps, maybe 10 to the 6, and then I'm going to have the x sample and the y sample. So I'm going to have here xy sample. This is the couple sample. Initially it's empty. And then I have x0. I have an x and y to be the initial point. So maybe I'm going to choose 0. I'm going to start at 0. And then I have the loop for I from 1, 2, and steps. And what I'm going to do is I'm going to generate a xp yp. So this is the proposal, this is the proposed move, and it's going to be x plus what? Well, it can be anything. But let's take a random displacement, which is uniform. So delta x is uniform between minus epsilon and epsilon, and dy is uniform between minus epsilon and epsilon. Okay, so what I'm going to do is that I'm just pushing the point by a random step in the x direction and a random step in the y direction, which is uniform over minus epsilon and epsilon. If epsilon is small, I'm just pushing randomly with a small amplitude. If epsilon is big, I'm just pushing randomly with a large amplitude. Okay, that's good. And then I need to accept that move. So if the uniform random number generator is smaller than the minimum between 1, and now what is Px? Px is uniform on the square. So here I'm just going to write it here. Px xp yp px y Then I accept the move, so the xy is xp yp. And then I put this add xy to the sample, so to the xy sample. And then within, I can actually calculate the estimator for pi, and then you'll see the estimator will converge slowly to pi. It will get closer and closer to pi. Okay, again, here the px is given to me. The px is, this is 1, 1 minus 1, 1, so this is 1/4 if x, y is in the square. It's 2 by 2, yes, and 0 otherwise. So this is my target distribution. My target distribution here is to be uniform in the square. So that's the target distribution. And so here I'm going to calculate the ratio of these two probabilities. You see that this will be 0 if the displacement is outside the square. You're not going to accept it. If you start inside the square, you will always stay inside the square because you will never accept points that will push you out of the square. Okay? So this relates to the epsilon. If epsilon is too big, it might actually push you outside the square, and then you're never going to accept those moves. And so this is not good because you're spending your computation time in rejecting moves. If the epsilon is too small, what you're doing is that you're just moving by small amounts, so you're always accepting the moves, but you're not moving much. Ideally, you want to cover this uniformly, so you want to actually move with sort of big steps, but not too big. Okay? And so this will determine how you choose that epsilon for the random displacements. So you need to experiment with this. You have to tune the epsilon to accept moves most of the time, but not all the time. And the prescriptions that people will actually use is that they want to accept move half the time. So the proportion of moves accepted should be close to 1/2. That's what people use normally as a guiding principle. Okay, there's no justification for this. It's just that your computational time is not spent rejecting moves and it's not spent accepting moves all the time. That's what it is. Okay, let me do another example because this method is so important that I think makes sense to try to understand it and see what you can do with it. Another example is to generate Gaussian random numbers using Metropolis. So this is an example that I have in the notes. I want the target distribution to be a standard normal with mean 0 and variance 1. What I can do is I can generate now the moves to be given by some points to which I add a displacement, and the displacement I'll actually choose to be uniform between -1 and 1. Okay? So this is interesting. I can generate Gaussian random numbers just by using uniform displacement. And the P of x in this case, the acceptance probability, will be the min between 1 and f x prime, whoops, it's p, px. And so in this case, it's the minimum between 1, and if I do this, you see it's the minimum between here, exponential of minus x prime square, and I'm going to have here, well, so in order to calculate the acceptance probability, you only take this exponential here for the target point square minus the point at UR square. This will give you a number between 0 and 1 because you're taking the minimum between 1 and this. This is always positive, by the way. And so you'll be accepting that move with that probability. And so you can put this on a computer, you run this for a very long time, you just collect all the points that you generate from the Markov chain, you generate the distribution, the histogram of those points, and then you'll see the histogram is very close to a Gaussian distribution. If your number of points is very high, like 1,000,000 points, the distribution will be very close to a Gaussian distribution. Okay, let's see if I have questions. Do you apply any conditions to confine x in the region in the square? In this example, no, because, well, the only condition is that I have to start in the square. So suppose I start in the square in the middle, then all the points that will be accepted necessarily will be in the square. Why? Because you see, the acceptance probability is the ratio of the target distribution, but the target distribution has no weight outside the square. So I want uniform in the square. So the distribution here will be, the ratio will be 0 if the proposed move falls outside the square. If it does, necessarily it will be rejected. So I will never accept points by construction outside the square. So it's built in the method. And that's because the target distribution has to be in the square. It has weight only in the square. Okay, if the target distribution is one-sided, then can the increment be function from a one-sided distribution? No. The P of x, the target distribution, can be anything. The P of x, the target distribution, does not need to be symmetric. What is symmetric in the metropolis is the displacement distribution. Okay, so the target distribution is P of x. This is what you want to sample from. This can be anything. What we consider in the metropolis is a basic random walk with symmetric displacement. This one has to be symmetric. Okay, but this is only a requirement for the metropolis algorithm. You can generalize this to non-symmetric displacement, and this is what's called metropolis Hastings. Okay, so again, Px is anything. It can be one-sided, no problem. For instance, you can generate variance according to the exponential distribution. You can do this using uniform -1,1 displacement, no problem. Suppose we are generating a density. Do we need to throw away a few initial points? Okay, this is a good question. This is about simulating a Markov chain and then reaching the stationary distribution. Remember that we are generating points like this, and then we can continue even to, we want L samples at the end. We start with some initial points. What you'll see is that if you sample the Markov chain and then collect those points and then plot the distribution of those points, you'll see that the distribution, the histogram, is not close to the target distribution. So the first few initial points are, the distributions of these points is not close to what you want. There's a certain kind of transient part of the Markov chain which you can throw away, okay? And then that's called the burning period. You might want not to consider the first few initial points in your sample, and you just throw them away, and you start collecting the points only after some long time. You can do this, but in many cases, you don't have to do this. If you collect all the points, it doesn't make a big difference in the way that the distributions of the points will be close to the target distribution. In the example, could you clarify how we end up calculating pi? Yes. So at the end, we have a bunch of random points, and if the metropolis was coded correctly, I have a bunch of points. I'm going to have XL of them. So I'm going to have, in fact, like 10 to the 3 or 10 to the 6. So I have many, many points. And what I do is I calculate an estimator. The estimator for pi is 4 times the number of points, and I just sum, and I count 1 if the point. So here actually I'm going to have, of course, I have points, right? So they're actually couples, x2, y2, and then I have also this one here. And here, it's the circle, it's the indicator function for the circle for that point. So this is equal to 1 if the point is inside the circle, and it's equal to 0 otherwise. So in the loop, actually, in the code, you could have a little if x, y, actually, you could have something like this. If x squared plus y squared is smaller or equal to 1, then you have your estimator plus equal 1, and at the end, the pi estimator will be 4 times the estimator divided by n steps. Okay, so that will be the estimator. This is how I update the estimator inside the loop, and then at the end, I just have that estimator. Okay, do the exercise. The solution is available, so it's all there. If we do want to throw away points, how do we count how many to throw away? So this is just, it's from experimentation. In Monte Carlo simulations that physicists do for equilibrium system, they do actually tend to throw the first initial points. And then how many points you throw is not, it depends on the application. There's nothing very general I can say. The goal in Monte Carlo always is to get more and more points. The bigger, the simple, the better. So Monte Carlo is funny because you want to spend the most time you can on doing your Monte Carlo simulation. So people actually doing simulations don't like people doing Monte Carlo simulations because if the computer is twice as fast, still people will be running simulations for the same time. It's just that they get twice the number of sample points. So I've been running simulations for a week, for a month, for 2 months, for 3 months, okay, just to get a large sample. And personally, I never throw away points because I don't know what's the burning period. But many people would do, and they tend to just throw away a fraction of points. Okay, so maybe they throw away the first 10% of points and so on. But there's no general prescriptions on this. It just depends on the application and how quickly the Markov chain will converge to the stationary distribution. The quicker it converges, then the shorter the burning period, so you don't have to throw points. If you know that the Markov chain converges very slowly to the stationary distribution, and sometimes it does, then you might want to throw more points. Okay, I think that's good. Okay, I think I'll stop on this topic, and I'll just, again, encourage you to do the exercises related to Monte Carlo in Chapter 2. In the Chapter 2 exercises, so the coursework number 2, you have many examples or many questions related to this, and then you'll get to see how it works, and then get to practice this. And as always, you have the Python code, so you can always refer there to guide you in writing your own code.
Sir, I have a doubt.
Yes?
For example, if P of X is very complicated in the sense like it has, let's say, multiple maximas,
Yep.
then if we do the Monte Carlo simulation, it probably won't reach the stationary because, I mean, would it definitely reach the stationary? I mean, at infinite time it might reach, but the question is there any better method to sample from a very complicated distribution?
Yeah, so this is exactly the case where burning one might be useful and where having very long simulations will be useful. When you're dealing with a very complicated PX that has many modes, it's very difficult to sample the different modes. And then even sampling a distribution that has 2 peaks is not so easy. So this is a good question, and it's something that's been studied quite a lot, and it's always a problem in Monte Carlo simulation. So suppose that your P of X is something like this. Then here it's a region of probable values, here it's a region of probable values, but when you do the random walk, in order to go from this region to this region, you have to go through a bottleneck. You have to go through a region of small probabilities. And so if you run your Monte Carlo simulation, what you'll see is that you get many points here. And so you're not really sampling the right distribution because you want to sample also that side. But it's very difficult for the Markov chain to reach the other side. Sometimes it will do, and then you start sampling on that side, and it's good, but then you want to come back to really sample the whole distribution. So there are many things to actually alleviate the problem here, but the first solution is just to make the simulation long. If the simulation is long enough, you will be getting on the other side and then you will come back. So that idea that Metropolis actually samples the distribution, the target distribution P in the long time limit is really true as a stationary limit. In the infinite time limit, Metropolis will sample P of x. But it's of course a question of, well, how quickly can I reach all these regions to reach the stationary distribution? And this will depend on the shape of Px. And also it will depend on how you build the Markov chain itself. So what kind of symmetric displacements you put there. Some choices of displacements might be better, might accelerate the way that you'll be sampling that distribution. But there are other techniques like tempering. Tempering is you actually have two independent simulations and then you swap them around, where you can have global moves. There are different ways to solve this problem.
About this only, just one more additional comment. Let's say we were distributing from Q of x, not distributing. These jumps were from some distribution Q of x. Suddenly change it to a different distribution. Such a move is accept. I mean, is it okay for a Markov chain? I mean, initially you sampled it for some like some jump probability distribution, and then you chase the probability distribution.
Yeah. You can change the Q with time. So I haven't discussed this, but you see the acceptance probability does not depend on Q. And that's the property of Metropolis. If you choose Qs that are not symmetric, then the acceptance probability will depend also on Q, and that's Hastings. So the acceptance probability does not depend on Q. So you can choose, even at each step, you can choose a different Q. So people do this sometimes. They do what they call adaptive Metropolis. So they have a Q with some parameter. For instance, I can do Metropolis with a given Gaussian distribution, and I change the variance over time. I can do this.
Okay.
It's used, for instance, in annealing and stochastic optimization. Okay, so we have 40 minutes now. So I think what I'll do is to move to the second topic, which is reversibility. So it's not a computational topic. It's a theoretical topic that has to do with equilibrium and non-equilibrium physics. And I think it might be interesting to some of you. With 40 minutes, I won't be able to go very deep on this, but I just want to give you, as always, pointers into the subject. And if you're interested, then you can read more stuff about this. Okay. So, I'll discuss reversibility in the context of Markov chain because it's just easier. So this is what I'm going to call this time reversal or reversibility. Reversibility of Markov chains. Okay, so we're going to start with we have a discrete time Markov chain. So we have a sequence of random variables like we've seen on Monday, which is determined by the transition probability that matrix by ij. And then I'll take the matrix to be time independent, so we're dealing with a homogeneous Markov chain. And then I'll assume, moreover, that it's ergodic. So assume homogeneous, and also ergodic. Okay, and then that part I, as always, is the probability of making a transition. And so this is the probability that to reach the state J if at the time before I am at the state I. And this is true for any n if the Markov chain is homogeneous. Okay, so that's the context. I have an ergodic Markov chain. What I want to determine is if I take a certain trajectory, so if I take a sequence of state and time and I reverse the order of those states, do I get the same probability or not? Okay, this is the idea of time reversibility. I think you know, but most of the laws of physics, like the laws of mechanics, are time reversible. If I record on video some physical phenomena that actually follows from classical mechanics without friction, and I reverse the video, I play you the video in reverse time, you're not going to see the difference because the physical laws are time invariant under reversal. If you have frictions, that's no longer the case. So if I put a ball down, it's going to bounce, but because of dissipation, it will get to stop. If I play that phenomenon in reverse time, it will look a bit bizarre because you go from a ball on the floor to a bouncing ball. So that for us is very unlikely, and then we feel that this is weird. The same thing, if I have a cup on the table, the cup drops and it breaks. If I play this in reverse time, it looks very bizarre because you go from a broken cup to a cup on the table. So many phenomena in nature are not time reversible, but we don't see them as the breaking of the time reversibility for those is not related to fundamental laws. They're related to statistical physics, and they're kind of an emergent phenomena related to entropy production or the increase of entropy in the universe. So it's quite a big subject. I'm trying to just put some context here. It's not so easy with the time we have, but you get the point. Some dynamical systems are time reversible, and some other dynamical systems are not time reversible. So when you reverse them, the trajectories actually are unlikely to be followed by the dynamical system. And then here you can ask the same question. If I look at trajectories that I simulate in the Markov chain, and I look at the probability of those trajectories but reversed in time, is the probability the same? Now to do this, I need to look at the joint probability. So if I have a sequence, so let me put this first. A trajectory in that context will be just a sequence of state. The trajectory, so I have transition probability, a trajectory. The trajectory, I'm going to write it like this. It's going to be this vector, and it's x1, x2, all the way to xn. Okay, so if you simulate the Markov chain, you can get n values in time. This will be a specific trajectory. Then you can redo the simulation, and then you'll get another trajectory. So this is the notation I'll use for the trajectory. And now the probability of that trajectory is given by the joint probability. The probability of the trajectory is the probability x1, x2, xn, and by the property of the Markov chain, this is the probability of seeing the first one times the transition probability from x1 to x2, etc., all the way down to pi xn minus 1 xn. Okay? We agreed on this. This is the Markov property. The probability of seeing a full trajectory is decomposed into fixing the probability of the first state, and then you multiply the probabilities for each of the jumps between the state and the next state. Good. Okay, so what I'm going to do now is to time reverse this. So this is the second concept that we need, time reversal. Here I have that trajectory, which is the forward trajectory. It's forward in time. You could simulate this on the computer. It's forward in time. I want to build now a new trajectory, which I'm going to build just by reversing the order of the states that I visit. So the time reverse trajectory, it's a transformation, so I'm going to call this x prime. This is, I visit the last state first, then I visit the second last, and then so on, and I finish with the last state that I've seen in the forward trajectory. So this is the backward backward in time. Okay, this is a transformation of the vector of trajectory. It's quite easy. I have the forward trajectory. I build another trajectory, which is just the same states that I visit, but in reverse order. So for instance, if I have something like this, suppose I have 3 time steps, and I visit this state, and then this state. This will be my xn. Then if I reverse this, it was going to be this, and this. So the first one, the white one, will be something like this, and the blue one will be something like this. Okay, it's a bit too much now on the same plot. Maybe I should actually draw 2 different plots. Let me do this, it's going to be clearer. This. Then in reverse order, what I'm going to see now for the x prime is first this, then this, and then this. Okay? So what is that forward trajectory now becomes that backward trajectory. The question is, what is the probability of this trajectory? Is it the same? Is it lower? Is it bigger? If you're simulating something and then you see it, it's because it's likely. So maybe when you time reverse it, it's unlikely. And this is the big question that you want to answer when you're dealing with this question of reversibility. So what's the probability of the time reverse trajectory? Well, we can find that probability easily. So the probability of the time reverse trajectory is, well, I first start with xn. So xn now is the initial state that I start with, and then I go from xn to xn minus 1, and then I continue like this all the way to x2, x1. Okay, and I've erased the probability of the forward trajectory, but it should be clear to you that the probability of the reverse is not the same as the probability of the forward, because I'm not calculating the pi elements in the same order. Okay, so this in general is not the same. In general. Okay, let's take an example here. Suppose I'm visiting 3 states A, B, C. The time reverse for this will be that I visit the C state first, then the B state, then the A state. So the probability of the forward would be, it's the probability of starting in A, then it's going to be the transition from A to B, and then B to C. That's the probability of the forward trajectory. The probability of the backward trajectory is the probability now of starting in C, and then the probability of making a jump from C to B, and then making a transition from B to A. And so in general, it's clear that it's different. However, and this is the main conclusion for that topic, if you have a certain condition satisfied by pi, then the forward probability will be the same as the backward probability. And that condition is what we call detail balance. Okay, so let me introduce that condition. 3, detail balance condition. That condition is a definition, so we're going to say that the Markov chain satisfies detail balance. I'm going to write this as dB with respect to the stationary distribution. So I'm going to write P star, right? And so I've assumed that the Markov chain is ergodic, so there's a unique stationary distribution. So detail balance is always defined with respect to a distribution, and here I'm going to define it as detail balance with respect to the stationary distribution if you have this little property. P star, you start at I and then you make a transition from I to J. This is the same as start in J instead and calculate the probability of doing a transition from J to I. This property is not satisfied by all Markov chains. Those Markov chains that will have this property are special, and they said to satisfy the condition of detailed balance with respect to P star. Okay. Now the main result is that if a Markov chain has this property, then the P forward is the same as the P backward. And this is what I want to prove now. Maybe I'll do this here. Let me actually change the board. This is a result, so proposition. If the Markov chain satisfies dB with respect to P star, then the probability of any forward trajectory is equal to the probability of the backward trajectory for any trajectory. Okay, and I'm going to do a little proof only using that ABC two-jump state. So the P reverse we've seen was P star C, transition from C to B, transition from B to A. Now, if I have this property, the detail balance property, I can flip those in order, instead of having pi of B to A, I want pi of A to B because I want to get to the probability for the forward trajectory. So here I'm going to have PC. By flipping this one here, I'm going to have PB, PC, and this will be PBC. So I've done a transpose, but by doing a transpose, I get new terms. So detail balance essentially is like a property that allows you to take the transpose of pi, but you get new terms out of it. And here I'm going to have P star A, P star B with the pi AB. Now you see there any cancellation, there's this, and so I get P star A, pi of AB, pi of BC. And that's the probability of your forward trajectory. Okay, so again, nice results. In general, for Markov chain, the probability of forward trajectory is not the same as the probability of the backward trajectories, but if you have this little condition of detail balance, the probabilities will be the same. So it means that whatever trajectories that you simulate, that trajectory is as likely to be seen if in reverse order. So if you simulate the system long enough, you'll see also those time reverse trajectories with the same probability, with the same likelihood. Okay, so that's the interpretation, and I think that's all the time that we're going to have. Oh no, maybe there's more time actually. So let me put the interpretation. So there are different ways that you can phrase the interpretation of that result. One is that directly forward trajectory and the backward trajectories, they have the same probability. So they're just as likely. Okay, so the Markov chain looks the same. Statistically, forward and backward in time. And that's the idea of reversibility. We say that the Markov chain is reversible. So sometimes you say the Markov chain is time reversible. What you can say also is that a forward trajectory is statistically indistinguishable from a backward trajectory. So if I give you a trajectory, you won't be able to tell if I was simulating that trajectory in forward time or in backward time, because forward and backward just have the same probability. They're just as likely to appear in the dynamics of the system. Okay. Any questions about this one? Okay, so this is a
Yes,
very... Yes.
one question. So for example, when we are using Monte Carlo Markov chain simulation for Brownian motion, but Brownian motion is a system which does not have time reversal symmetry. So
No, it
do
doesn't.
we mean that? Do we mean that we don't imply the detailed balance condition there, or it doesn't matter?
Again, what's the question?
So for simulating Brownian motion model using Markov chain Monte Carlo, do we not impose the detailed balance condition?
Let's be careful here. When we're simulating Brownian motion, we don't use Markov chain Monte Carlo, right? So the simulation technique that I presented yesterday for Brownian motion was just a direct simulation of Brownian motion. What I presented today with Markov chain Monte Carlo with Metropolis is how, for instance, to generate a Gaussian, but I haven't seen how to use Markov chain Monte Carlo or Metropolis to generate paths of the Brownian motion. Actually, we have to distinguish these two things. They're totally different. Okay? So when we do Metropolis, we're not using Metropolis to simulate any Markov processes. We're just using a Markov process to do some kind of calculation, to get some estimate. So Brownian motion is not reversible, that's true, but it's got nothing to do with Metropolis.
Okay.
Okay? And the way that the recipe we've seen for simulating Brownian motion is just as it is. It's not reversible, but that is the recipe for simulating Brownian motion. There's no problem with this. So some stochastic processes are reversible, some other are not reversible. And what I've seen and what I've shown here is how to define reversibility for a discrete time Markov chain. What I don't have time to do is you can extend all these concepts for a continuous time Markov chain and also for a diffusion. So you can take a continuous time path and time reverse it. So instead, for instance, I can look at a path of Brownian motion or a path of a stochastic differential equation, and I can reverse that path. Now, I've taken the worst path to time reverse, but let's take a path like this. Okay, and with some noise, imagine that you have some noise, then the time reversal of this will be something like this. Okay, and the question is, this is the forward trajectory, I can calculate its probability. What is the probability of the backward trajectory? Is this a likely or unlikely path? If the stochastic process is reversible, these two paths will have the same probability. And so I can extend this notion beyond Markov chain in discrete time to continuous time, even continuous space. Okay, and there's no way, I mean, this will be like a course in itself to actually explain this. More questions? Don't you require all probabilities in your station distribution to be non-zero for the proof to go through? Yes. Yes, and this is a good point. You see, the condition of detailed balance has, it's this, right? The probability to go from I in a jump I to j is the same as the probability for j to I. But it's actually built in the fact that these probabilities will be non-zero because the chain will determine its own stationary distribution, okay? And the chain will determine a stationary distribution which will have non-zero components. So the zero components will be trivially satisfied, there's no problem, and then you can divide things, like it's just like 0 equals 0. And then, but for the non-zero values, you're gonna have something like this. Now, if it's non-zero to be at I and your chain is ergodic, it will be non-zero also to be at j. So there's no way you can get non-zero equals 0. the stationary distribution will make sure that that condition is satisfied, if it is satisfied. So if a Markov chain does not have a stationary distribution, we cannot have detailed balance. But all MCs with detailed balance will have a stationary distribution. I think this, when I have to think about this, I think the statement is partially true. A Markov chain having detailed balance with respect to some distribution will have that distribution as a stationary distribution, but it doesn't mean that the Markov chain is ergodic. Now, any ergodic Markov chain satisfying detailed balance with respect to its unique stationary distribution, well, here's ergodic. I guess that's just trivial. I'm just repeating really myself. But yeah. So I guess the only thing I can say is that if the Markov chain satisfies detailed balance with respect to some distribution, that distribution is a stationary distribution. But there might be more than one stationary distribution. So you can have a Markov chain that has this condition of detailed balance with respect to many distributions. Then all these distributions will be stationary distributions. Now, the crucial property of Metropolis is detailed balance. Metropolis is reversible. Metropolis has that detailed balance condition. Okay, and this is part of the coursework number 2. You have to prove this in coursework number 2. Okay, let me finish.
Hi, just 2 questions. So when you're proving this probability for the forward and the reverse trajectories to be same, like you're sampling initial conditions from the stationary distribution, right?
Yes.
That is crucial.
Yes. So when I define detailed balance, I'm always saying detailed balance is with respect to a distribution. Here I've chosen to be that distribution to be the stationary distribution. And what I want is I want to start the Markov chain with that stationary distribution. Okay, because that's the detailed I want to use.
So another query actually. So suppose I have a Markov chain which doesn't satisfy detailed balance. So I can classify trajectories into sort of pairs, like one is forward and one is backward, depending on like which has more probability. Is it possible to construct a conjugate dynamics, some sort of tilted dynamics where the reverse trajectories with respect to the first dynamics is like actually more probable with respect to the second dynamics, auxiliary dynamics or something?
Yeah, you can do this. So actually, this is what I want to do, and I'll finish with this. So this is a good question. It actually, it just like ties in now to the last topic I want to discuss, which is the notion of a time reverse process.
Okay.
What we've done so far is actually we haven't changed the Markov chain at all. What we've done is that we're taking a Markov chain, we're imagining some trajectories of that Markov chain, and then we're asking, are the time reversal of those trajectories likely or not likely? If we have detailed balance, then any trajectory that you can simulate, and then you time reverse that trajectory, that reversal will have the same probability. So forward and backwards have the same likelihood. But we're not discussing now changing the Markov chain itself as a time reverse Markov chain. But you can imagine doing something like this. So this is, I'm going to finish with this. This is the time reverse process. So what we've done again is that we had a Markov chain, we have a forward, we changed this to a backward trajectory, and then we're comparing the probability always with respect to the same Markov chain. So when I calculate this probability, I'm really asking, what is that probability with respect to the Markov chain itself? Okay, so this is the first step we can do, and this is what we have done. What I want to do now is I take the Markov chain as a sequence of random variables, and I do a time reverse operation to define now a new Markov chain that has different transition probabilities, and those different probabilities will correspond to the probabilities of the time reverse trajectory. Okay, and how I do this? This Markov chain will have now a new transition matrix that will be determined by now P prime, and the trajectories for those P prime will be the probabilities with respect to the original matrix for which you actually generate. Okay, so maybe that's a bit confusing here. What here I'm doing is I take a trajectory, I time reverse it, and I can calculate the probability for the forward, and I can calculate the probability for the backward. But this is not P prime, this is P. So this is the law of the trajectories for the original Markov chain. What I want to do here is to define a new Markov chain, and whatever trajectories that I put here, I want the probability of those trajectories, and the way I define those probabilities is the P prime for a trajectory is the P for the time reverse trajectory. So this is how I define a transformation of the stochastic process. So here I'm going to put this again. Okay? This is actually how you transform fields in classical mechanics or in electrodynamics. The new field is at some point is the original field at the transform point. Okay, so what we're doing is that we're just raising this thing to now define a new Markov chain with those P prime probabilities. And so that means that I'm going to have a pi prime matrix. How do I calculate the pi prime matrix? Well, I just have to expand this. This will be the probability to start. So this will be the P with respect now to the time reversal. So this will be the original probability at the last point, pi xn to xn minus 1, just like we had before. But this doesn't have the form of a Markov chain. What I want to do is to write this as some P prime for the initial state, and then some pi prime with x1, x2, all the way down to some pi prime xn minus 1, xn. Okay, so this is how I want to define the P prime. I want to define the P prime via a new transition probability that will have the states in the correct order. This is the definition, but you see the states appear in the reverse order. Now you can show that, I'm not going to do the calculation, the full calculation, but what it ends up is that this pi prime ij will be 1 over pi I, the pi ji, and here the pi j. So I think this relates to the question, because now this is a transformation of the original pi. I think the word tilted was mentioned, and indeed you can see this as a tilting, but this is now the matrix, the transition matrix for the time reverse process. Okay, so the time reverse process is just the probabilities of the time reverse trajectories of the initial process. That's what it means. And in general, you see this is not equal to pi ij. But if you have detailed balance, it is equal to pi ij. So if you have detailed balance, the pi prime matrix is the same as the pi matrix. The system is reversible, so the time forward process is the same statistically as the time backward process. In general, you don't have this. And this relates to the question that we had on Monday. This pi prime is not equal to the pi minus 1. So the backward dynamics of the process is never given by pi minus 1. Okay? Pi minus 1, in fact, in general, does not exist. The true backward process is this pi prime. Okay, so that's the transition matrix of the backward process. So maybe I should write it here. This is the forward process, the forward Markov chain, and this is the backward or the time reverse Markov chain.
That definition of this time reverse dynamics, what is that PI? Is it the stationary distribution of the forward process?
It doesn't have to be, but in many cases it will be. If I'm dealing with an ergodic, then this is what you choose. But whatever distribution that you choose to begin with, you will define the backward process with the distribution that you start with.
Oh, I see. Thanks.
Good. Okay, so I think this is a good time to stop. There's a lot more. This is a very rich subject. And again, I'm not even touching now reversibility for continuous time and continuous space, which is very interesting too. Even for an SDE, you can define from a forward SDE, you can define a backward SDE. And it's got a different drift, it has the same noise, it's an SDE still. And then some SDEs will be reversible and some SDEs will be non-reversible. The gradient SDEs that we've seen are reversible, and then we call them equilibrium. When something is not reversible in physics, we say that they are non-equilibrium. So sometimes you have steady state non-equilibrium state, it's like steady non-equilibrium states. You can model those using a Markov process that doesn't have the detailed balance condition. So in physics, often we actually equate detailed balance with equilibrium. And if you break detailed balance, we say that this is non-equilibrium. There's a question, I missed the argument between pi minus 1 not existing. Well, you can just check this actually. Pi minus 1 does not exist in general. It doesn't exist for Markov chain because pi is a contraction in the space of distribution. So from many initial distribution, you get to the stationary, so you cannot have an inverse. But the point I was trying to make here is that the backward process, if you reverse time, is not defined by some inverse of the matrix pi, it's defined by that pi prime. So pi prime is the transition matrix for the time reverse process. So this notion of pi minus 1 doesn't have any meaning.
Hi, so this pi tilde definition doesn't seem like it's a stochastic matrix unless until like Pj is the stationary distribution, right? When I sum over j on both sides. How to prove that pi tilde is a stochastic matrix? It looks like it's only if p pi is p, right?
You have to check it. I need to sum over j. So I need to sum over j. Some properties there might be true. So, but I think you can define this in many ways. I don't think it's true only for the stationary. You can define this for non-stationary too. But yes, we need to check. That's a good point. I believe this matrix is always stochastic, but it needs to be checked.
Yes, certainly. If P is a stationary distribution, it satisfies the stochastic property. Otherwise, it doesn't look like. Yeah.
Well, for P stationary, I think it is. I think what's happening here is that when it's not stationary, the pi matrix is actually not homogeneous. So maybe I have to take this into account. Okay. Okay. So again, there's lots of material behind this. Unfortunately, there's not a single textbook explaining this. Except for detailed balance related to Metropolis, for instance. So there's some aspects of reversibility that you can see in textbook, but I have never found one textbook where this is clearly explained. And in fact, I'm working with a colleague to try to write a textbook on reversibility, but this is going to take some time. So if you're interested on this, then you can just drop me an email and I'll put some references, and then I'll try to put those references also in the Dropbox or on the website, and so you have access to this. Good. Questions? I think I can go back to my normal camera here.
Yeah, Hugo, so I have a bit more like a naive question related to this time reversibility. So I think, so in this definition of time reversibility, it seems that we need the Markov process. But if we take, for example, anomalous diffusion process or non-Markovian, we could still think of equilibrium of those. So do you think it would, one could think of a definition of equilibrium as some process which are just time reversible without, because the definition for just time reversibility doesn't require it to be Markovian or not.
No, you're right. Yeah, so The basic property of reversibility, if you want to define it for general stochastic processes, is just to have forward trajectories having the same probabilities as the probability of backward trajectories, whatever the process is.
Yes.
Here on the board, what we've done is that we've used the Markov property to relate this to detailed balance. But in principle, you could define reversibility for non-Markovian.
Yeah, so for example, yeah, if you think of fractional Brownian motion and you put it in a potential, it will reach an equilibrium state, but we don't have a detailed balance sort of.
Yeah, you're right. But then I think one has to be careful because fractional Brownian motion could reach a stationary state, right? So I think the crucial word to begin with for any processes is whether you have a stationary distribution. Then you might want to characterize it further by having time reversibility or not time reversibility. But whether you want to call this equilibrium or not is something else. So I think one has to be careful when you say it reached a distribution which is equilibrium. Would it not be better to call it just stationary to begin with and then study time reversibility in a general
Right, so
sense?
once it reaches stationary state, then you say whether it now in the stationary state, if the trajectories are time reversible. And then my question is, would that be a more less ambiguous definition of equilibrium, which would not require it to be, like which would generalize the sense of equilibrium to also to non-Markovian processes? Would that fair to say? Or
I think
there's something wrong? Or
I think you can in principle, but you'll lose a lot actually, because then you'll lose the connection with currents.
yes.
See, the notion of current is only relevant for Markov processes. And then what's interesting for Markov processes is that detailed balance is related to non-zero currents in a Markov process. If you look now at a non-Markovian process, there's no notion of current, and there's no notion of locally conserved currents or things like this. Mm-hmm. So I think you could define reversibility in a global trajectory sense, but then you lose many kind of physical connections that you might want. But yeah, I've never seen this actually, but I think it's an interesting question.
Okay. I had one more question, if I could ask, so which was something to do with this Markov chain Monte Carlo method. So there's something which I always get confused with. So you see, in your algorithms, you've discussed that you may need to wait a bit long to reach, for the system to reach you. So you see, but when I start in my simulation, I start from a configuration, and that configuration already appears even when the system is in the stationary state. And if I evolve, it would, if it is an atypical configuration, it would very fast reach to the very probable one, and then it would explode. So it seems that I don't, in this way, when I think of it, I don't need to wait for anything to reach stationarity, because I'm starting with just a configuration and not a probability distribution. And very fast it will reach a most probable, and I'm just sampling in a time average sense. So I don't even need to wait anything. Is that a part do you think makes sense? Because
yes, but it depends. It makes sense, but I think it depends on that initial condition. The thing is that you may start your system with a fixed initial state, which is in a region far away actually to where the stationary distribution is concentrated. When you say that the point actually reaches a typical state quickly, it does depend on the Markov chain. So some processes, like imagine actually you want to sample Einstein-Uhlenbeck process, but you start the Einstein-Uhlenbeck at the point 10,000. Then we know most of the weight is around 0. It's going to take some time for the 10,000 to actually decay to 0. And the further away you take the initial point, then the more time it will take to reach a region close to 0. Okay. But there is a relaxation, and the relaxation is given by the second eigenvalue of the transition matrix.
Yes, so that's what so the relaxation, the gap usually goes as some system size L square or something. But the confusion that for me is always in my head, that I see that if I follow the trajectory, it seems it reaches the most typical one rather fast.
Yeah, well, I think but the relaxation might not be fast. Like if you have, for instance, a spin like Ising, and then you look at very low temperature, but with some field. So let's put the field up. So like typical configurations are all pointing at low temperature, they're all pointing up in the direction of the field. But suppose your initial condition now is all the spins pointing down. It's going to take a very long time before you actually reach stationarity in that case.
Right. Yes. So in those cases, well, yes, when there is a barrier.
I agree with you. In most simulations, at least in the simulations I've been doing myself in research, I've never used any burning. There is a quick convergence, but it might be because I haven't studied phase transitions where that thing actually tends to happen and show up. Yeah.
Okay. Okay. Thank you.
Good.
Hi. Can I ask some question actually, which yesterday you partly answered? Then, so it's about like sampling some correlated random process. So you mentioned that you can sample the correlated random process like by constructing some auxiliary dynamics such that the realizations of that process can serve as samples for sampled according to this correlated process. So I was wondering, like, is it always possible? I mean, is there any prescription to construct this dynamic such that, like, for example, like, if I want to generate like colored Gaussian noise, I can simulate maybe a Langevin equation in a harmonic potential or something to get like color noise with certain characteristic. So, I mean, in a general sense, like, if I want to sample like some distribution of that sort, like some colored distribution or something of that sort of multivariables, is there any prescription to construct these auxiliary dynamics such that its trajectories give my samples from this distribution?
Not really. So I don't think there's a general prescription. The idea is there. So if you want to generate something which is correlated in time and non-Gaussian, then what you can do is to generate something which is Gaussian white noise in a higher dimension, and then you just project the higher dimensional process to a lower dimensional process, and that the projection usually introduces correlation and non-Gaussian distribution. So that's the general idea, but how you implement this in practice to get specific correlation and specific distribution is difficult, and I don't think there's any general prescriptions there. So for instance, for all the color noise, we have recipes for those. So we know how to generate brown noise or pink noise or any kind of noise that has a given spectrum. And that's usually done, as you mentioned, by simulating some Einstein-Lembing process in some higher dimension, and then we just project one of the random variable, one of the state, and so that state now is correlated in time, and so it's colored. But if you have any arbitrary correlation and distribution, then I wouldn't be able to say what the enlargement or the enlarged process should be. This is a difficult mathematical question. It's not even clear that there is a recipe or an answer. I think it depends. It's a case by case thing. It depends on the problem.
Okay, thank you very much.
There's a questions from Alberto. Are pi and pi j appearing in the equation for pi, the stationary one? It doesn't have to be. Then if they're not, they would depend on the step of the process, and the process wouldn't be homogeneous. Exactly. So if you start something which is not stationary, if you start something which is stationary, then the time reverse process is also stationary. There's no problem. But if you start the process, if you have a stationary process, but you start it from something which is not a stationary distribution, then the time reverse process will be non-homogeneous. I wish I could do some examples with you, but we don't really have time. It's a bit more difficult, but time reversal in general will make a homogeneous process non-homogeneous. So that pi, well, I'm pointing here, but oh yeah, I'm pointing with this camera. Pi prime is typically non-homogeneous.
Hugo, I have a question. See this P of X here, what you have taken, it need not be equilibrium, right? I can take any P of X and drive by this equilibrium dynamics, and I'll reach that state, right?
You mean for the metropolis?
Yeah, to do the Markov chain Monte Carlo, I can even take a non-equilibrium steady state and generate. But when I drive this by this equilibrium dynamics, whatever this state I have, by definition, I have a Hamiltonian correspond to this, right? So does it mean that for any non-equilibrium steady state, there is an equivalent of Hamiltonian in the equilibrium system, basically, right?
And it's because, so the other way I could phrase it is that if I want a Markov process with a given stationary distribution, there's an infinite number of equilibrium and non-equilibrium Markov process that will have that stationary distribution, that ergodic distribution. So to say that a process is equilibrium or non-equilibrium, it's not only based on its stationary distribution, you need another conditions to determine this, and that's detail balance. So a system with detail balance and a system without detail balance can have the same stationary distribution. Where they will differ is in the current. So there's another notion that I haven't discussed this week, but you know that notion. We can define now a stationary current, and the non-equilibrium system has a non-equilibrium current, and the equilibrium system has a zero stationary current. But yet they have the same stationary distribution. And so you're right. So you can sample a non-equilibrium distribution using an equilibrium metropolis scheme. There's no problem in this. It's a different process. It has nothing to do with...
You'll not get the non-equilibrium properties, basically.
Yeah. So if you want to simulate the current as well as the stationary distribution, then you can't use metropolis.
So are there any more questions? If not, let's really thank Hugo.